18 is helium. So you see here, if we see the general electronic configuration of group 13 elements, it is NH2 NP1. So we have the s orbital fulfilled. So this is the picture of the s orbital, let's say. And if we have these electrons, so both these electrons are upfilled and in the opposite spin pairing. And we have 3 p orbitals. You all know, like p orbitals are 3 in number. They are px, py, and pz. So in case of group 13, there is only 1 electron in the p orbital. That is this. So there is only 1 electron in case of boron and the subsequent members of group 13. The same, if we calculate the electron for the group 14 elements, so it will be carbon. So it will be NS2 NP2. So NS orbital will be fulfilled, but we will have 1 more electron in case of carbon. Likewise, in case of nitrogen, for group 15 elements, we will have 1 more electron. That will be NH2 NP3. So likewise, we will add up the electrons. But what will happen when we'll add 1 more electron? That's in case of oxygen or group 16 elements. So in case of group 16 elements, we are having 4 electrons. So here you might have read about this Hund's rule. So Hund's rule is nothing but it dictates how the electrons will be filled in the orbitals. So Hund's rule states, if we have some library of orbitals, suppose these are the orbitals here, and Hund's rule says how to fill up the orbitals by the help of electrons. So according to this rule, the electrons will one by one fill up in the same spin. So firstly, if we are having 5 electrons, it will go by this. But when we are having 1 more electron, suppose we are having 6 electrons, so then the 6th electron will come to the first orbital, and that will be in the opposite spin. So the 6th orbital electron will come in this, or the 6th electron will come in the opposite spin. So their spin pairing will cancel the electron momentum. So that will be the same, will be applicable in case of group 16 elements. We are having NP4. So 1, 2, and 3. So 1 more electron will come and will pair with the first electron, that is the px orbital. Likewise, in case of group 17, we are having 5 electrons. So the 5th electron will come in this py orbital. And in case of group 18, that is the noble gas elements, we are having 6 electrons. The 6th electron will come in this orbital. So you are seeing this NH2 NP6. So this one is NS2 and this one is NP6. So that is the configuration of this noble gas element. But in this chapter, we will be specifically discussing about the first 2 groups, that is the group 13 and group 14. So you see, the first group, that is the group 13, is having the first element boron, and group 14 has the first element as carbon. Now, there is a trick by which you can understand how to define or assign the oxidation state for the elements of each groups. You see, first one is the group 13 element. So the oxidation state, that is the most common for the element, will be +3. For group 14, the oxidation state will be +4. For group 15, the oxidation state will be +5. For group 16, it will be +6. For group 17, it will be +7. And for group 18, it will be +8.
मैंने लिखा S1 अब यहाँ S1 की बात S1 क्या है एक स्ट्रक्चर है ये डेटा स्ट्रक्चर बनाया S1 का पहले क्या है S1 डॉट x y z और S1 डॉट क्लियर इस तरह S2 हो जाएगा S3 हो जाएगा इस तरह क्या होता है डेटा सेव करते हैं क्लियर तो देखा आपने किस तरह से स्ट्रक्चर बना रही है अब मैंने बोला S1 की आईडी है मतलब तो ये अब स्टूडेंट है इसके 30 पैरामीटर पैरामीटर कौन से होंगे कि आईडी और नेम और 30 आईडी के लिए नाम है
কি কথা বলে যাচ্ছে সমানে
ये आपका नाम आ गया ये क्या है इसके पास करना पड़ेगा या उसके अंदर
So there is a trick by which you can understand how the exact element will be assigned to their corresponding oxidation state. So if it is a group 13 element, then the general oxidation state will be +3. So these 3 will come here. This 4 will come here. This 5 will come here. And likewise, this 18 will come here. So whatever be the group of the element will be, suppose we are talking about carbon or you are talking about this phosphorus. So you don't know what is the oxidation state of phosphorus, the most common oxidation state. So you just have to remember which group potassium or phosphorus falls into. So phosphorus is nothing but this coming under nitrogen. So nitrogen, phosphorus, arsenic, antimony, and the last one is bismuth. So nitrogen comes from the group 15. So they are all group 15 elements. So group 15 elements will have, the phosphorus is coming from group 15. So phosphorus will have the oxidation state +5. So this is not the sole oxidation state of phosphorus. Phosphorus may have some other oxidation states, but this is the most common oxidation state of phosphorus. Likewise, this group 13 elements will have this group oxidation state +3. These 14 ones will have +4. 16 will have +6, and so on. There are several other oxidation states for each group also. You see, for group 13, we are having oxidation state +1 also. For group 14, we are having +2 and -4. For group 15, we are having +3 and -3. For 16, we are having several oxidation states, +4, +2, and -2. For group 17, there are more oxidation states, +5, +3, +1, and -1. And group 18 elements, that is the noble gas elements, they are having +6, +4, and +2. So you should note a fact here, like the oxidation state will be diminished by a multiple of 2 only. So by a multiple of 2x, the oxidation states will increase or decrease. Suppose you are saying for group 13, So group 13 is having oxygen state of +3. So the other oxygen state will be just we are having 2x less or 2x more. So either it will be 2x plus or it will be 2x minus, where x is equal to 1, 2, 3, and so on. So here you can see, like for group 14 element, the most common oxygen state is +4, and one of the least commons are -4. So if we subtract +4 from -4, we are having a mod value of 8. So 8 is actually a multiple of 2. So x is 4. So here also it can be written as 2 into 4. So just as the trick that I have told you, so if we have to remember about the oxygen state or the abnormal oxygen states of each group, you just have to remember about the main oxygen state of the group. Suppose we are saying for oxygen for it is group 15. So the most common oxygen state will be +5. So it is group 15. So +5, it will be having +3, and it is having also -3. So if we start from the fact that it is only 2x plus or 2x minus, so from +5, we can go to +3, we can go to -3. So from +5, if we have to go to -3, we have to jump by a factor of 8. And if we have to go from 5 to 3, we have to jump by a factor of 2. So both 2 and 8 are multiples of 2, where x is 1 here and x is 4 here. So for any group, just by the method that I have told you, you can calculate how many oxygen states are accessible for the element. You see here, for example, it is for group 16 element, the common oxygen state is +6. So if we subtract 2 from 6, we will reach +4. Again, by subtracting 2, we will be having +2. Again, by subtracting 4, we will reach -2. So in all the cases, either we have to subtract 2 or 4 or 6 or 8. So multiples of 2 are actually required. So by 2x multiples, addition or subtraction, we can reach the other oxygen states of each element or each group. You can also apply the same rule here also. So for group 17, the most common oxygen state is +7. So if we subtract 2, it is +5. Subtract 2 more, it is +3. Subtract 2 more, it is +1. And subtract even more 2, so it is -1. So just by subtracting or adding the multiples of 2, we can get the several oxygen states of each group. And if we reach group 18, then also from +8, if we subtract 2, it will be +6. If we subtract 2 more, it will be +4. And if we subtract 2 more, we will reach +2. So just by adding or subtracting the multiples of 2, we can actually reach about the different oxygen state of each metal or each elements of the p block elements. So coming to the next part, so first one is we will discuss about the group 13 elements. So we will discuss about this group 13 elements, that is the boron family. Since the first element is boron, so that's why it is termed as the boron family. So group 13 elements can be depicted as boron family. So boron has boron, aluminium, gallium, indium, and thallium. So these are the main elements of this boron family: boron, aluminium, gallium, indium, and then thallium. So the first question is, BF63- is non-existent, whereas AlF63- is a stable molecule. So we have to rationalize the statement why it is so. BF63- molecule does not exist. So let me write this for you. This is boron hexafluoride 3-. And we are having this aluminium hexafluoride species, that is AlF6 3-. So this is species 1 and this is species 2. So according to the question, BF6 3-, the species 1 is non-existent. But the second species, that is AlF6 3-, is a stable molecule. So we have to rationalize the statement. So you, first of all, we have to here can answer by the analogy of the metal size or the orbitals. So you can see here boron is having the electronic configuration 1s2, 2s2, 2p1. So we are having 1s2, we are having 2s2, and we are having 2p1. So let me fill up the electrons for you. So first one is the 1s orbital. Here there are 2 electrons. Then we are having 2s orbital, where you have also 2s 2 electrons, and this is the 2p orbital. So here we have only 1 electron. So this is the electronic configuration or structure of boron molecule, boron atom. Now, if we excite this 1 electron to this 2p orbital, we are having 3 electrons separately. So in the excited state, we are having 3 electrons for boron. These 3 can bind with the electrons that are derived from the fluorine atom. So that's how BF3 molecule is formed. So this is how BF3 molecules are formed. These X daggered electrons are actually designed to see the electrons of fluorine, and this one is the electrons from boron. So thus 3 fluorine atoms will each give 1 electron, and thus this BF3 molecule will be formed. And then we will have this vacant 2p orbital that will be like this. That is actually vacant, because you see here 1 orbital will be vacant. This electron will come to this orbital. So this orbital will be vacant. So we will denote it as 2pz. Now, we are having BF6 3-. So we are talking about BF6 3- molecule. So for BF6 3- to form, we have to add 3 more fluoride anion. So BF3 will add up with 3 fluoride ion to generate this BF6 3-. But you see only 1 orbital is actually here vacant, because for quantum, the principal quantum number 2, there is no d orbital. So 2d is actually impossible. In your structure of atom chapter, you might have encountered these facts, like 2d is impossible because d actually starts from 3. D starts from 3. So for aluminium, 3Ds are actually available. But for boron, there is, since boron's principal quantum number is 2, there is no d orbital. So this boron cannot accommodate these 3 F- ions to it. Rather, it can only accommodate 1 F- to the vacant p orbital. So that's why boron forms BF4-. So BF4- is existent, because in the vacant p orbital, boron can accommodate 1 F- anion. So that's how BF4- can be formed. But in case of aluminium, there are d orbitals. So d orbitals can easily accommodate these extra F- ions. So we can form AlF3 quite easily, just as we have formed BF3. But since aluminium is having these d orbitals 1, 2, 3, 4. So 5 d orbitals are actually vacant. So here 2 of the orbitals can be accommodated by the F- ions. That's why AlF3 can form AlF6 3- quite easily. It is a very stable molecule. But in case of boron, it can form BF3, or maximum it can form the BF4 minus, that is the tetrafluoroborate anion, but it cannot go beyond that. So that's the answer here. So in this question, I have elaborately explained how BF6 minus cannot be made possible. So in a nutshell, the answer will be non-availability of the d orbitals does not allow boron atoms to expand its octet. Hence, maximum number of covalent C shown by boron is 4, that is BF4 minus. Now we will go to the next question. So the next question says as, why do white fumes appear around the bottle of anhydrous AlCl3? So AlCl3 is very stable molecule. It is one of the most commonly applied Lewis acid in chemical laboratory. So AlCl3 is having this structure. It is anhydrous, which is having anhydrous means it is having no trace of moisture. So there is no water present in anhydrous AlCl3. It is only AlCl3. Since they are actually highly Lewis acidic in nature, so these aluminium 3+ centers tend to capture the water molecules around itself. That's why AlCl3 can be found in the nature in two different appearances. One is the hydrated AlCl3, another one is the anhydrous AlCl3. So what happens when we open the bottle of anhydrous AlCl3? So there is a bottle. Suppose this is a bottle. Okay. And in the bottle, we are having this AlCl3, which is solid. Now we are having moisture in the atmosphere. In rainy season, the amount of moisture content in the atmosphere is actually quite high. So whenever we are opening the bottle of AlCl3, this AlCl3 comes into contact with the moisture. So what happens? Since I have told Al3+ centers are highly Lewis acidic in nature, so they tend to capture water molecules from the atmosphere or the ambience. So what happens? Al3+ centers will capture the water, that is the water molecule, and it will get hydrolyzed. So hydrolysis means some water molecules will come and attack on our compound and it will degrade that. So what happens in this case? In that case, AlCl3 will be hydrolyzed, and the hydrolyzed product will be AlOH whole 3. It is the hydroxide of the aluminium, and from the same reaction mixture, HCl gas will be liberated. Now you know HCl is actually a gas. The HCl that we use in our laboratory is actually the aqueous solution. That is, the HCl gas is actually made soluble in the aqueous or in the water. But actually HCl is a gas and it has some white fumes. So whenever we are opening the bottle of AlCl3, the Al3+ centers will get hydrolyzed by the moisture that is present in the atmosphere itself. So that hydrolysis will trigger the formation of HCl, that is the hydrochloric acid gas. Now this moist HCl gas is appearing white in color. That's why whenever we are actually seeing the bottles of anhydrous AlCl3, we will see white fumes that will appear around the bottle of AlCl3. So coming to the next question, what happens when borax is heated? So you should actually read more about borax, because borax is one of the major compounds in this group 13 or the boron family. So borax is this one. This is the Na2B4O7.10H2O. This compound is called as borax. So borax, you can see that is having 10 molecules of water in its crystal. Now, borax bead test is one of the major tests to detect about the certain metal ion in a sample. You might have encountered or do the practicals in your laboratory like the borax bead test. So borax bead test is actually one of the major tools to see whether our sample has which kind of metal or the cation. So this is borax. So whenever we are heating this borax, this delta sign is actually a denotion of the heating sign. So when we are giving thermal energy to borax, it will lose these 10 molecules of water. So these 10 molecules of water will be evaporated whenever we are applying heat. So when this heat is applied, these 10 molecules of water will be expelled out, and we are having this anhydrous Na2B4O7. So now if we heat this anhydrous Na2B4O7 more with more heat, then these reactions occur. So you are having this NaBO2, some metaboride, and we are having this B2O3, that is the boric anhydride. So whenever Na2B4O7 will be heated more, so this metaborate compound is formed, NaBO2 and B2O3. That is the anhydride of the boric acid. So boric acid is nothing but BOH whole 3. And B2O3 is nothing but the anhydride of the boric acid. So B2O3 is boric anhydride, it will be formed. So whenever borax is heated, ultimately we are left off with NaBO2 and B2O3. The last question in this slide is why is orthoboric acid considered as a weak acid? So orthoboric acid or boric acid are essentially the same. We can denote orthoboric acid as H3BO3, or we can also say it is BOH whole 3. So both are actually same. I will write this equivalent sign here to show that both of these are actually termed as orthoboric acid or boric acid. So why is orthoboric acid considered as a weak acid? Now, whether an acid is strong or weak depends upon its ability to release the H plus ions. So suppose we are having a species AH. So if it is releasing A minus, and it is also releasing H plus. So depending upon how strong or how efficiently it can actually expel this H plus, on this factor depends upon the acidity of this AH molecule. Now, more the A minus will be stable, more the AH will be producing A minus, so the more H plus will be produced. So it all depends upon the stability of the A minus species, that is the conjugate acid, or in case it is conjugate base. So if it is acid, A minus, it is conjugate base. So depending upon the stability of the conjugate base, the acidity of a specific species will be determined. Now we are having this orthoboric acid. Now it is considered as a weak acid. So it is actually not able to release H plus ion efficiently. You can see here it is the B boron. So what is there in case of H3BO3? In case of H3BO3, we are having this BOH bond. Now, if it releases one of the H plus, we will have this BO minus species. Let me erase the other part to show you these things clearly. Okay. So here you can see we are having this acid as BOH whole 3, it is actually having other OH whole 2. So I will encircle this species. It is BOH, and from this we are going to BO minus. Now O minus is an anion. It is the oxide anion. So the more O minus will be stable, the more acidity will it show. But you see, boron is having electronegativity of 2. In Pauling scale, boron's electronegativity is only 2. So it is not an electronegative element. So if it is not an electronegative element, so electronegative elements means which? You should know about electronegative elements. Electronegative elements are those elements which can actually pull the electron towards itself. And electropositive elements are which can actually push the electrons from themselves. So boron is having the electronegativity of only 2. So what are the electronegative elements? Electronegative elements are fluorine, chlorine, oxygen, nitrogen, and there are several others, but these four are some main electronegative elements. Now these electronegative elements can actually stabilize the anionic charge because they can actually drag the charge on themselves, so they can stabilize the negative charge. But in case of boron, the electronegativity is only 2. So boron atom is not able to stabilize the negative charge that is already formed on the oxygen. That's why BOH whole 3 is not actually able to release H plus ion on its own. That's why boric acid is considered as a weak acid. But how this boric acid can actually showcase its acidity? Now we will go to some concept of Bronsted acid and Lewis acid here. So this is the concept of Bronsted acid. So Bronsted is one of the pioneer scientists in this field who actually developed this kind of acidic system, that is the Bronsted acid. But there is another method that way we can also show, or we can also assign that these are the acids. These are the Lewis acid based concept. So in terms of Lewis theory, the acids are which that can actually accept electron. And bases are those which can actually donate electron. So in case of Lewis theory, A is the acid that can actually accept electron, and B is the base that can actually donate electron. But in case of Bronsted theory, the acid-base concept is not the same. In case of Bronsted theory, the molecules that will be able to produce H plus will be considered as acids. But in case of bases, the molecules which will be producing OH minus will be considered as bases. So in case of BOH whole 3, that is the boric acid, So in case of boric acid, what happens? Boric acid is actually able to accept the OH minus from the water molecule. So this OH minus is actually nothing but electron. So in case of Lewis acid concept, boric acid is an acid because it can accept electron. And why it is so? Because I have already told that is the boron is having a vacant p orbital. So if it is having a vacant p orbital, in the vacant p orbital, electrons can come. That's why boric acid is a Lewis acid, not a good Bronsted acid. So what happens in this case? Boric acid is actually able to drag the OH minus from the board of the water molecule to form this tetrafluoroboric acidity ion, that is the BOH whole 4 minus, and in turn it actually releases the H plus. So that's how boric acid shows its acidity. So boric acid is not a typical Bronsted acid, it is actually a Lewis acid in nature. So by the help of its Lewis acidity, it can showcase its acidic nature. So the next question is regarding what happens when diborane is treated with ammonia. So diborane is nothing but this B2H6. So B2H6 is one of the very well-known compounds in case of this group 13 elements. Diborane is having this structure as B and another it is having B. And in the terminals, they are having 2 hydrogen atoms for each boron. On the other boron also, the structure is also similar. So we are left with 4 hydrogens. So to complete the BHB, this B2H6, we will have to add 2 more hydrogens. So here it is 1 hydrogen, another one is this hydrogen. So you can see here that is 2 BH3 molecules are actually coming into picture to form a cluster type of species. So we are having this interaction between this hydrogen and this boron, and also there is an interaction between this boron and this hydrogen. So whenever this is the typical structure of diborane molecule. So in diborane, you can see that there are actually 3 centers, 1, 2, and 3. But there is no formal bond between this hydrogen and this boron. So only 2 electrons are there from this bond. So we are having these 3 centers, but 2 electrons. So it is a 3C, 2E. In the lower part also, you can see it's a 2 borons and 1 hydrogen atom are there. But there is no formal bond between boron and this hydrogen. But the 2 electrons are coming from this boron hydrogen bond. So if we see this BHB linkage, we are also having this 3C2E. So from the upper linkage, you are having this BHB as 3C2E, and from the lower linkage also, we are having this 3C2E. So the terminal boron hydrogen bonds are normal bonds that are called classical bonds. They are also always 2C2E. This B2H6 is such a beautiful molecule. It has some butterfly kind of structure. And if we see the terminal BH bonds, they are actually 2-centered 2-electron bonds. 2 centers, one is the boron, another is the hydrogen. 2 electrons are there, so 2-centered 2-electron bonds. But in case of this middle bridging hydride cases, there are actually 3-centered 2-electron bonds. So we are having 4 2-centered 2-electron bonds in case of B2H6 and 2 3-centered 2-electron bonds in B2H6. So in case of B2H6, the geometry and also the bonding is actually quite interesting. So whenever B2H6 is actually treated with ammonia, what happens? So first of all, this acid-base adduct actually forms. You know, all the boron atoms are actually, boron compounds are Lewis acidic in nature. So, and this ammonia is having 1 lone pair of electrons on the ammonia. So ammonia is the Lewis base. And B2H6 is the Lewis acid La is actually Lewis acid and Lb is the Lewis base. So this Lewis acid and Lewis base will react. You know, like the Bronsted acid and Bronsted base reacts. Suppose you take HCl, that is a Bronsted acid, and you treat it with NaOH, that is a Bronsted base. So you know, whenever a Bronsted acid and Bronsted base comes into picture, they react readily to form NaCl and water. So they produce salt and they also generate water. So Bronsted acids and Bronsted base react with each other. Here also Lewis acids and Lewis base will react with each other. So you see, one hydrogen is actually, boron is actually able to drag one hydride from the ammonia. So it will be BH4 minus. And we are having BH2 NH3 whole 2 plus. So we are having this salt, this plus minus salt. This is the cation and this is the anion, just like NaCl, Na plus and Cl minus. So this is an analogy from the Bronsted theory. So this cation is actually analogous to Na, and this anion is actually analogous to Cl. So this BH2 NH3 whole 2 plus and BH4 minus is a salt between a Lewis acid and a Lewis base. Now what happens when the reaction is performed more? We are having 12 moles of hydrogen will be liberated, and we are left with this compound, this B3N3H6. B3N3H6 is one of the very well-known compounds, and it is one of the majorly utilized compounds from the group 13 elements. So B3N3H6 has a nickname called borazine. So this is called as borazine, or it has some other names as inorganic benzene. So let me draw you benzene for this. So here, if we draw benzene, you all know about the structure of benzene. So benzene is nothing but C6H6. So this is benzene. Benzene's molecular empirical formula is C6H6. And this one is called the inorganic benzene, B3N3H6. So you see, the number of hydrogen atoms are actually same, but number of carbons are actually divided. So C6 we can denote as C3 and C3. And if we have a look in the periodic table, we are having group 13 element as boron, group 14 element as carbon, and group 15 element as nitrogen. So if we are having equal numbers of carbon, so we have to divide the number of carbon between boron and nitrogen. So if we are having 6 carbons, so 3 will be taken up by boron and 3 will be taken up by nitrogen. That's why whenever we are having C6, we have to divide the factor by C3 and C3, and now we are left with B3 and N3. And H6 is the same. That's why it is called the inorganic benzene, because it is having inorganic molecules, inorganic atoms. Boron and nitrogen are inorganics. That's why it is termed as inorganics. So boron is an inorganic atom, not like carbon. That's why in case of benzene, just like the analogy of benzene is having the molecular formula as C6H6, but this boron will have the molecular formula borazine, will be possessing B3N3H6. Since boron is one atom before carbon and nitrogen is one atom after carbon, that's why we are having this C6 designated as B3N3. So B3 and N3, that will be confirming the C6, and we are having H6. So just in the alternate positions, we will be having this boron and nitrogen in case of borazine. That will be the structure of borazine. So synthesis of borazine is actually very, very important for your exam. You have to remember the balanced equation, how this borazine will be formed from ammonia. The question will come as such, how you will prepare borazine from B2H6. So this will be the answer. So of this slide, the next question is, how can you explain the higher stability of BCl3 as compared to TiCl3? Now, down the group, because of the poor shielding effect of the intervening D and F orbitals, the effective nuclear charge will actually get increased. So what is the case? So let me show you with a specific example. First one is the boron. Now we are having this aluminium. Now we are having in gallium, indium, and in the last we are having thallium. Now we are having this case. So here down the group, because of the poor shielding effect of the intervening D and F orbitals. So whenever we are going down the group, D orbitals will come into picture, F orbitals will also come into picture. And we all know the shielding effect of D and F orbitals are very less. They cannot shield. That's why the nucleus, the effective nucleus, is actually exert more power or more tightness on the electrons. So we are having this nucleus and we are having these electrons. Now, whenever we are going down the group, because of the poor shielding effect by the D and F orbitals, the electrons will be more tightly bound by the nucleus. That's why it will not allow the NS electrons. So the NS orbitals are actually closer, but NPs are actually away. S orbitals are actually more closer to the nucleus. So the NS electrons will be more tightly bound to the nucleus. That's why it will not be involved in bonding. So you see, if NS electrons are more tightly bound to the nucleus will not allow them to bond with the other atoms or other metals or other species. But the NP electrons will be actually NP1. NP1 electrons will be available for bonding. That's why only one oxidation state will be favorable in case of the molecules which are actually downward. That's why for the heavier congener TEL, the +1 oxidation state is more favorable. Whereas for the lighter element, that is the case of boron, this shielding effect is not coming into picture. In that case, the +3 states will be more accessible or more feasible. So these are the main questions of the group 13 elements. Now we'll come to group 14 ones. So the group 14 elements, first question is, consider the compounds, that is the BCl3 and CCl4, boron trichloride and carbon tetrachloride. How will they behave with water? Now, I have already told, like, the B is the group 13 element, which octet is actually not fulfilled. Now, since the octet is not fulfilled and it is having only 6 electrons, that's why it can accept electron from the water molecule. So it has, boron atom has vacant 2p orbital. In the vacant 2p, boron atom can accept electron from the water molecule because it is a Lewis acid. It is a Lewis acid. So since it is a Lewis acid, it will react with water and it will get hydrolyzed, just like LCl3, and it will produce orthoboric acid, and also HCl will be formed. But same is not in the case of CCl4, because you see CCl4 is the carbon is the group 14 element and it has octet fulfilled. So 8 electrons are actually fulfilled in case of carbon. Now carbon is actually having principal quantum number 2. That's why it cannot expand its octet, because 2D is impossible. So D comes from the 3 principal quantum number. Since the octet cannot be expanded, since there is no vacant d orbital, that is, water molecule cannot attack on H2O, on this CCl4, because it has no vacant space. That's why CCl4 remains unaffected by water. But whenever we are having BCl3, BCl3 gets readily hydrolyzed. Now, the next question is explaining why there is a phenomenal decrease in the ionization enthalpy from carbon to silicon. First one is there are two reasons here only that can be actually used to answer the question. The first one is the appreciable increase in the atomic size from carbon to silicon. So here we have carbon, here we have silicon. We then have germanium, then we have tin, and at last we have lead, that is Pb. Now from carbon to silicon, if we go, we are having an increment in the atomic size. Now carbon has electronic configuration 1s2, 2s2, 2p2. So 1s is actually here, then 2s, then 2p. But in case of silicon, the electrons are actually fulfilled. We are having 1s2, then we have 2s2, then we will have 2p6, then we are having 3s2, and then we will have 3p2. So we are having this intervening or electrons here, 1s2, 2s2, 2p6. So here in case of silicon, we are having these many electrons in the middle. That's why they will produce this efficient shielding of the outer electrons by the inner 2s and 2p electrons. That's why you will see they are having s and p orbitals are actually very good shielder. Actually very good shielder. S and p are actually have very good shielder. So the nucleus will not be able to drag the s2 and p2 electrons. That's why these electrons will be very much vulnerable. So the nucleus is not actually able to bind the electrons too much tightly of the silicon, then it will be easy to expelled out. That's why very much less energy is actually required to pull off the valence electron of silicon. That's why if we go from carbon to silicon, there is a drastic decrease in the ionization enthalpy. In case of carbon, the value is actually reaching around 1000. But in case of silicon, the value is around 750 only. So you see, if we go from this carbon to silicon, because the inner electrons are actually very good shielder, these 2s2, 2p6 electrons are actually produce very good shielding effect. That's why the nucleus is not actually able to tightly bind the valence electrons of these group 14 elements. That's why there is a decrease in the ionization enthalpy. The next question is thermodynamically the most stable form of carbon. It is actually an informative question. You don't have to have any kind of concept here. Just it is very important for the exam purpose. That's why I and fluorine. So you should know carbons can show very much a number of allotropes because of the catenation property of carbon. It can form several carbon-carbon bonds. And now all these compounds are actually allotropes of carbon, diamond or coal, graphite, fullerenes. So among which this graphite is the one that is having the thermodynamically most stable form. That you have to remember for the exam. Graphite is the most thermodynamically stable allotrope of carbon. The next question is classifying the following oxides as neutral, acidic, basic, or amphoteric. So neutral means it does not affect, it gets affected by acid or affected by base. Acidic means it actually reacts with base. Basic means it actually reacts with acid. And amphoteric means it reacts both of acid and base. So amphoteric oxides are those which react both with acids and bases. Neutrals are one that can actually does not react with neither acid nor base. Basic ones react with acid and acidic ones react with base. Now the acidic oxides are B2O3, SiO2 and CO2 because all these actually react with base. Basic one is the Tl2O3 which actually reacts with acids. Amphoteric one is actually PbO2 that actually reacts both with acids and bases. And carbon monoxide, that is CO, is actually neither affected by acid nor affected by base. That's why it is called a neutral oxide. So these are the major questions that we have to discuss in the group 13 and 14 elements. So here I have actually encountered some practice questions for you that you can actually examine on yourself. The first one is the whether boric acid is a protic acid justified. In my Lewis acid concept theory, I have actually told what is a Lewis acid and what is a Lewis base. So these are the specific hints to the examples. The second one is the drawing the resonance structures of carbonate and bicarbonate anion. So carbonate is nothing but CO32 minus. So CO32 minus, we are having carbon, we are having 3 oxygens. So first one is this one, and another oxygen is having a negative charge. So this is the carbonate. So this electron will pull off here and this will be dragged by this oxygen. So thus you can draw the resonance structure of carbonate. The second one is the BCl bond has a dipole moment, but why BCl3 molecule possesses a net zero dipole moment? So the hint is actually there in the geometry. BCl3 molecule is planar and it is trigonal. Now you can answer whether all the bonds are actually having some dipole moments, still the molecule does not possess any dipole moment. The next question is regarding why the BF bond lengths in BF3 and BF4 minus differ. That actually I have discussed in the first question, like how from BF3, if BF3 takes up one fluoride ion, it will produce BF4 minus. Now you can understand how this is geometry can be changed from this trigonal planar molecule to the tetragonal or the tetrahedral molecule. So boric acid is polymeric due to which reason? You might have known the structure of boric acid, that is BOH3. Now BOH3 can actually form extensive hydrogen bonding, intermolecular hydrogen bonding with other BOH3 molecule. So that's how it is a hint how they can form a kind of some kind of this extensive structure, polymeric structure. So these are the actually basic practice questions for you guys to go through this chapter, and you should be able to answer if you read about this question. Both 13 and 14 block elements are now over. So in our next class we will be discussing on the group 15 and group 16 elements, that is the group nitrogen and group oxygen elements. So that's the point we'll stop.